Welcome to this pre-recorded presentation. The topic is spatial factor modeling, a Bayesian matrix normal approach for misaligned data. This is a joint work with my PhD advisor, Sudipto Banerjee. Since I will give a short talk, I will skip a lot of technical details. You can check the link on the last slides to see the archive paper of this project. You are also welcome to send me any further questions through the email address listed on the slides. The motivating data of this project is a large-scale spatial dataset. I summarized some key features on these slides. We have 10 responses, 2 explanatory variables. The number of observed locations is over 1 million, and the dataset has misalignment. Not all variables are recorded on every observed locations. On the right-hand side, we give a heat map of counts of observed variables. On each observed location, we use a colored dot, with color representing the counts of response. The greener the color, the higher the value. In the middle, there is a red square. This is the zone we pick for prediction. The dataset has misalignment over 65% of observed locations. One of the responses is NDVI, which is an index to identify vegetation amount in the measure plant health fatality. NDVI ranges from -1 to +1. The higher the value, the higher amount of vegetation it represents. We first shape NDVI's range to 0 to 2 and transform it by log for better model fitting. And the NDVI helps to understand the global distribution of vegetation types, as well as their biophysical and the structural properties and the spatial variations. Red reflectance is also one of our response. As we know, healthy green plants can absorb red light. So on area with high amount of vegetation, we tend to observe low red reflectance. We give the color map of transformed NDVI and the red reflectance on the slides. The left-hand side is for NDVI and the right-hand side is for the red reflectance. The study domain is a zone located around the western United States. The two colored maps on the slides are in the same color scheme. The warmer the color, the lower the value. So as you can see here, along the northern part of the coast, we observe high value of NDVI and a relatively low value of red reflectance. So our data, our response, have a spatial pattern and they have some inner correlation with each other. We want to fit a multivariate spatial regression model. Here we denote all response on location S by YS and the corresponding explanatory variables by XS. Then the multivariate spatial regression model models the response factor by a linear combination of explanatory variables plus omega s, the latent process, and the epsilon s, the noise process. We assume epsilon s is IID across different locations, and the latent process here can capture the underlying spatial pattern that cannot be explained by explanatory variables for all responses. So the inference of the latent process on all the observed location helps to interpolate the response on the location with misalignment. And it can also provide the information of potential predictor and help the researcher to find further research topics. Omega S is typically modeled by a zero-centered Gaussian process defined with a cross-covariance function C. The cross-covariance function defines the covariance matrix of latent process on any pair of location in the study domain. To work on a Bayesian multivariate spatial regression model, we need prior for beta and sigma, and the product of the distribution of beta sigma, the distribution of the latent process, and the likelihood is proportional to the posterior distribution of all parameters. With that, we can get the posterior inference of all parameters through methods like MCMC algorithm. However, fitting Bayesian multivariate spatial regression model with our target dataset can have big data problems. So when we calculate the distribution of the latent process on all the observed locations, we need a Cholesky decomposition of the covariance matrix of the latent process. For n observed locations Q response, the covariance matrix will be an NQ by NQ matrix. Even for Q equal to 1, n equal to 1 million, the estimated storage of the decomposition of such a huge matrix would be over 3,700 gigabytes in RAM, and it can take up to hundreds of hours for an i7 processor to do the decomposition. It's even more challenging for obtaining Bayesian inference when using iterative method like MCMC algorithm. There are many studies on scalable spatial modeling, but most of them focus on single process modeling. There is a very limited discussion on scalable multivariate spatial data modeling, especially for data with misalignment. So we want to extend scalable modeling strategies for a single process to Bayesian multivariate process modeling. First, we built the latent process from univariate models. We modeled the cross-covariance function of our latent process by linear model of coregionalization LMC. Through that, we can reformat our latent process in terms of univariate process. Here, we model omega s by lambda transpose times fs. The lambda transpose is a Q by K loading matrix, and fs here is a vector with K elements. Each element follows a random field with covariance function rho K, and all the elements are independent to each other. These slides give the LMC model. Here we color all the parameters we want to get posterior inference in orange, except for F, which is hierarchically modeled by a zero-centered Gaussian distribution, and we let it depend on a hyperparameter set psi k. We need to find the prior for the rest of the parameters. Here we define gamma as regression coefficient matrix beta aligned with the loading matrix lambda. And then we need to find prior for gamma, sigma, and the hyperparameter set psi k. We assign a matrix normal inverse Wishart as a prior for gamma and sigma. Matrix normal inverse prior is a distribution defined on a space of two matrices. One is positive definite. In our case, it's sigma, and it follows the Inverse-Wishart distribution. The other one, given this positive definite matrix, follows a matrix normal distribution. A matrix normal distribution is defined through three parameters: the mean matrix and the two other positive definite matrix. When we vectorize our target random matrix, it follows a Gaussian distribution centered at the vectorization of mean matrix, and it has covariance matrix equals the chronicle product of the other two parameters. Matrix normal inverse Wishart is a conjugate prior for matrix normal distribution. On this slide, we give the Bayesian LMC model. Here you can assign any prior for the hyperparameter set psi k. There also exists other Bayesian LMC model, but our model yields conditional posterior distributions in a closed form for all but the hyperparameter set psi k. Our model is also very flexible. We can restrict sigma to be diagonal and replace the Inverse-Wishart distribution by inverse gamma distribution for the elements of sigma. And when the number of independent process k is less than the number of response, our model becomes a factor model. With the closed form of conditional posterior distributions, we can design a block update MCMC algorithm. And we can show that the most of the univariate scalable spatial modeling strategies we can use to model the elements in FS can facilitate the whole block update MCMC algorithm. We illustrate a factor BLMC model with diagonal sigma with our motivating data. Here we choose k equal to 2 since we observe a high correlation across different response. And our univariate process fk here is modeled by nearest neighbor Gaussian process, which is a scalable spatial modeling method. The sampling process of a MCMC chain with 10,000 iterations costs around 75 hours on a Linux machine with i7 processor and 33 gigabyte of RAM. We give the interpolated map of latent process plus intercept for transformed NDVI and the red reflectance. We can see here that the latent process keeps the major spatial pattern while it smooths out some details. And it also smooths out the prediction on the picture region. So in summary, we provide a model that can implement scalable multivariate modeling methodologies in Bayesian multivariate spatial data analysis. Our methodology features that obtaining a posterior inference of the high-dimensional latent process, and we facilitate the posterior sampling process through the conditional conjugacy brought by using matrix normal Inverse-Wishart. Thank you.